In this video, we're going to discuss the solubility of gases. So there are two major factors that affect the solubility of gases. And here, we're specifically talking about the solubility of a gas in a liquid solvent. So for example, if we're dissolving a gas in water. And the two factors that affect the solubility of a gas in a liquid solvent are the temperature and the pressure. So let's start by discussing the effect of temperature. The solubility of a gas in water tends to decrease as the temperature increases. So if we look at the graph over here, we have the solubility versus temperature. You can see that as we increase the temperature, the solubility tends to go down. And that's, of course, because as we increase the temperature, the gas particles move faster and they're more likely to escape or be released from the solvent, which in this case is water. And we have some examples of that, of course. If you leave a carbonated beverage, which is carbon dioxide dissolved in water, if you leave that out at room temperature, it's going to become flat because the carbon dioxide will escape. But if we store it in the refrigerator where the temperature is lower, that carbon dioxide will tend to remain in the water for longer. Also, if we have warm lakes, they have less dissolved oxygen in them than cool lakes. The other factor that affects the solubility of a gas in a liquid solvent is pressure. The solubility of liquids and solids in water, for example, does not change with pressure. However, gases are affected by the pressure. The solubility of a gas in a liquid is directly proportional to the pressure. So that means as we increase the pressure, you can see over here in the figure, if we increase the pressure, we're essentially forcing down on the piston, increasing the internal pressure. So if we increase the pressure, then the solubility of the gas will increase. We'll get more gas dissolved in the liquid and vice versa. We can calculate the solubility of a gas using Henry's law. And Henry's law tells us that the solubility of a gas is proportional to the pressure. So as we said before, if we have a gas in here in a sealed container, we have the gas, the partial pressure above the liquid, and then we have some gas dissolved in the liquid. If we increase the pressure, we're going to get more gas particles moving into the liquid, so we're increasing its solubility. Now with Henry's law, the C sub G represents the solubility of the gas, and we generally express this in molarity. Moles of gas dissolved in our solution divided by the volume in liters of the solution. K is Henry's constant, and it's specific for a particular gas in a particular solvent. So K, our Henry's law constant, depends on the solute, so what gas we're talking about, the solvent, whether it's water or some other solvent, and the temperature of the solution. So if we change any of these, our Henry's law constant for that substance would change as well. And you can see the units here, moles per liter times atmospheres. And P sub G is the partial pressure of the gas above the liquid. So let's take a look at a problem. We're given the Henry's law constant for methyl bromide, which is a gas used to fumigate soil, and it's 0.159 moles per liter times atmosphere at 25 degrees Celsius. What is the solubility of our gas in water at 25 degrees Celsius with the partial pressure being 125 millimeters of mercury? So pause the video and see if you can solve this problem. Okay. So the first thing I would notice is that here we're going to use Henry's law to determine the solubility of our gas, and we're given the constant and the partial pressure. But we have to pay attention to our units. K here has units of pressure in atmospheres, and our partial pressure is given in millimeters of mercury. So these two must be in the same unit. So we're going to change our partial pressure into atmospheres. So we've got our partial pressure of our gas in atmospheres. Now we can plug it in to our Henry's law, and we have our K value here and our partial pressure here. Notice that our units of atmospheres will cancel and we'll end up with moles per liter or molarity. So therefore, for this gas under these conditions, we would be able to dissolve 0.0261 moles of our gas per liter of solution.